This is Neil Patwari. It's ESE 471. This segment is on 5 important frequency transform properties that you're going to be using in communication systems design. For all of these, I'm going to assume we have a continuous time aperiodic signal. And let's take that continuous time aperiodic signal to be x of t. It's going to transform to be x of j omega. The first property I'm going to talk about is the time shift property. The time shift property states that the Fourier transform of a time-delayed signal, a signal delayed by t0, is equal to this complex exponential multiplied by the original Fourier transform. So the complex exponential is e to the minus j omega t0. You can think of the minus t0 multiplying by this regular complex sinusoid e to the j omega. And that's what we get out of the time shift property. It is a phase shift. A time delay corresponds to a phase shift that is a function of the frequency and the time delay. The second property I want to talk about is the scaling property. Okay, the scaling property says that if I take a time-scaled version of the original continuous time signal, that is x of at, then my Fourier transform becomes 1 over a. The a is only the positive part, the absolute value, multiplied by the Fourier transform, but instead of omega in the transform, I replace omega with omega over a. And here the a does not have an absolute value over it. Again, remember, if a is positive, we're making the signal go faster or narrower in time. And when we divide by a in the frequency domain, we're making the frequency representation spread out, and of course be multiplied by this constant 1 over absolute value of a. The third property I want to mention is the convolution property. The convolution property says that if I have a signal x of t and another signal h of t, in this case I use h of t as a channel impulse response. If I'm convolving the signal with the channel impulse response, the output is going to be the frequency domain version of the signal multiplied by the frequency response of the channel. The fourth property I want to talk about is the modulation property. The modulation property says that if I multiply a signal x of t with a cosine at a particular frequency omega naught, that the Fourier transform will be 1/2 of the signal centered at frequency omega naught in the frequency domain, plus the signal centered at minus omega naught in the frequency domain. So if I have x of j omega looking like this, then in the frequency domain, when I look at the Fourier transform of the signal multiplied by a cosine, then I'm going to have the signal looking like this. The signal is identical. Sorry, I may not have drawn that triangle the same, but the same triangle in each part of the negative frequency axis and the positive frequency axis. This would be half of the magnitude, so if this is 1, then this would be 1/2. Essentially, this is the property of modulation that we talk about when we're going to send the signal on a channel at a certain frequency. This is what we're talking about. The fifth property I want to mention is Parceval's theorem. The energy of a signal is the same in the time domain as in the frequency domain. What I want to do, instead of talking about these examples, which again you should look in the Rice book and in my notes for more detail about the statement, especially Parceval's theorem, integrating the squared magnitude of the signal in the frequency domain versus the time domain. But for an example, I wanted to talk about using some of these properties in an example problem. Here I'm going to talk about a pulse shape that we develop using a convolution of different pulse shapes that are easier to describe. The example is, what is the frequency domain content of a pulse shape x of t generated from the convolution of a rect function with itself 4 times? That is, that x of t is equal to y of t convolved with y of t convolved with y of t convolved with y of t, where y of t is this rectangular shaped function that is 1 between minus t over 4 to plus t over 4 and 0 otherwise. Y of t looks like this in the time domain. It is 1, value of 1 between t over 4 and minus t over 4, and it's 0 everywhere else. Okay, that's why I'm calling it a rectangular function. We have a rectangular function that is on our Fourier transform table in the Rice book. This function, rect, so let's take that as a given because it is in a table, and let's try to derive what the Fourier transform is of x of j omega, given that we have this particular Fourier transform relationship and we have the properties that we discussed above. So first, we can convert x of j omega, which we want, because we have the convolution property. The convolution property says that the Fourier transform of the convolution is going to be a product of the individual frequency domain representations. This is just y of j omega to the 4th power. Now, what is y of j omega? Well, we can write it in terms of a different rectangular function, this rect function. So we're going to write y of t in terms of the rect function. To get the time domain signal to be scrunched in time, take a shorter duration, we're going to have to multiply time to make time go faster, right? To shorten that duration of that rectangular function. If I take 4 times t as the argument, then when 4t is equal to minus t, then that's the first time the value goes to 1. That is when t is equal to minus t over 4. So we are getting this function that we drew for y of t. Okay, so this means that I can apply the scaling function to compute what y of j omega is. It is a time-scaled version of rect of 4t with a constant a equal to 4. Remember, it's 1 over the absolute value of a multiplied by the Fourier transform of that rectangular function. So I'll call that rect of j omega, but then with the omega divided by the constant. In other words, I'm going to get 1/4 and then plug in the 2t sine of omega divided by 4. Here I'll write it as omega t divided by 4, and then omega t divided by 4 in the denominator. And so what I'm going to see, plugging this back into the x of j omega expression, I'm going to get this is our solution, and we've applied 2 of the properties of the Fourier transform, and that's how we get our answer.